Let us now talk about what's often called the cosmic concordance. What's really meant by that is an agreement between all various methods converging to the same values of cosmological parameters, which, needless to say, never happened in the past. Usually, this is expressed in the diagram that plots omega matter on x-axis and omega vacuum, or omega lambda, on the y-axis. On that plane, flat universe is a straight line at slope of minus 45 degrees because the two always have to add up to 1 for a flat universe. Note that there are also models in which there is no Big Bang, where a cosmological constant is so large that it prevents the initial singularity. So in this diagram, we can plot error contours of different measurements. The cosmic microwave background one is an error ellipse nicely aligned with the flat universe line. The supernovae Hubble diagram is almost orthogonal to it. We can also make dynamical measurements of omega mass from clusters of galaxies or from baryonic acoustic oscillations, and those tend to be almost vertical. Mercifully, they all seem to converge and intersect at one place, and that place is on the flat universe line. This is where omega matter is a little less than 0.3 and omega vacuum is a little more than 0.7. So remember, if we look at supernovae alone, they suggest that there is a omega vacuum or cosmological constant, but they by themselves alone do not tell you that the universe is also flat. From the microwave background alone, we can certainly tell that the universe by itself is flat, but not how the omega matter and omega lambda are distributed, although one can get probability distributions for those. If we then add measurements from large-scale structure, which probe the dynamics, then altogether they intersect in the same place. And so the point is that various methods of measurement, completely different methods of measurement, converge to the same thing, which is what gives us some faith that indeed these are correct interpretations, that we do have finally measurements of the cosmological parameters. Note, however, that in most tests there is a degeneracy between parameters. You can trade one for the other a little bit in a particular direction in this parameter space. So in cosmic microwave background, that's fairly obvious that there are all these elongated error ellipses. And generally speaking, for any one of these tests, you get probability density contours in some sort of parameter space, and there is a best fit value, but that need not be the actual best answer. And the product of these probability clouds has to really converge to the most likely overall value of the parameters. Generally, this is done through Bayesian statistical approach, especially for the microwave background measurements, and it involves a lot of computations and Monte Carlo simulations, but it's a process that's well understood. Also, if you can declare values of some parameters known, that immediately narrows down probability distributions for others. For example, you can take value of Hubble constant that's derived from Hubble Key Project and fix that, and then you get a better answer for the omegas. So here is an example of probability distributions for various parameters from a paper by Tegmark et al. That includes all of these data together. And you can see that for most of them, what's obtained is not a sharp value of a parameter, but rather an extended distribution. You can then project these probability density distributions in various parameter space planes. And for example, here is one that shows Hubble constant expressed as little h versus omega of matter. The big red regions are regions that are excluded using WMAP observations alone. Then the other sources of measurement, like Hubble Space Telescope and so on, intersect, and you find out that indeed all of the probability distributions peak out at one common value. It's not a sharp value for sure, but it's a much narrower distribution than otherwise would be. And here is our concordance plot, now shown a little differently. The red regions again are excluded by the WMAP measurements alone. the orange regions by their improved analysis. If they add measurements from large-scale structure from Sloan Digital Sky Survey, then that goes further down. And then finally, if they also use supernovae, that narrows the error ellipse right around that magical set of values of 0.7 and 0.3. Here is another one where Hubble constant is plotted against total omega. And total omega seems to converge to unity. Universe is flat, with Hubble constant again having the same range of values as we've seen before. Or one can ask the question in terms of the age of the universe and omegas, and here we have a plot that shows error contours of this. So different colors, remember, correspond to introduction of ever more observational constraints. Red from just original WMAP data alone, orange for better analysis, yellow including large-scale structure, and finally using supernovae. Now recall the equation of state parameter W. For pure cosmological constant, that is exactly -1. So here is the plot of error contours of W against omega. And there is a fairly broad distribution that's allowed, but subsequent measurements got that narrower down to -1. Another quantity that can be estimated is the number of neutrino species, interestingly enough, because neutrinos do contribute to energy density in the early universe in a similar way that photons do. So here is again the concordance plot as shown earlier. Various methods together make estimates of cosmological parameters sharper, and they always do converge to the same set of values of omega matter a little less than 0.3 and omega vacuum or omega lambda a little more than 0.7. A great deal was made out of this as the discovery of dark energy, but this is perhaps overstating things a bit. Cosmological constant's been with us for a long time now, and astronomers have considered it seriously to explain more or less the same problems. And here's, for example, a title page from a paper in Nature by two famous astronomers, Jim Gunn and Beatrice Tinsley. They introduced cosmological constant for more or less the same reasons. The astronomers invoked it later in 1990s to reconcile what otherwise would be discrepant measurements of Hubble constant and the density. Here is a simple concordance diagram I myself made as a graduate student, maybe 13 years before the supernova results were announced. We didn't have a supernova Hubble diagram then, but one could use lines of equal age of these models and choose the set that's roughly what globular clusters give you, and that turns out works just as well as supernovae. So that too pointed out that if you wanted a flat universe, as say demanded by the inflation theory, then you must accept solution whereby density is really only around 0.3 and cosmological constant is around 0.7. So to recap, our best guess universe parameters today is that the age is about 13.7 billion years. The Hubble constant is just a tad over 70 kilometers per second per megaparsec. That the density of baryons, normal matter as we know it, is around 4% or 4.5%. That the total matter density, including the dark matter, which is not baryonic, is about 0.27. And the energy density corresponding to the dark energy, possibly cosmological constant, it makes up the rest of about 0.73. So let's just look at three key densities. The total density, again expressed as fraction of critical density, which is close to 1, the matter density, and the baryonic matter density. Interestingly enough, if we just add up all the luminous matter that we see in galaxies, stars, radio emission from gas, and so on, that only adds to like 0.5% of the critical density, much less than the total number of baryons that we know. And so, because 0.5% is less than about 4%, there has to be some sort of missing baryonic matter, and that was an interesting problem in of itself. And because 0.04 is less than 0.27, there has to be a non-baryonic component of matter, which is the dark matter. And because 0.27 is less than 1, there has to be dark energy in order to fill up the rest. So to recap the cosmological tests, they always based on comparing some kind of measure of distance versus redshift. And in order to do this, we use test particles of different kinds. If we have objects of ostensibly equal luminosity, those are standard candles. If we have objects of ostensibly same size, those are standard rulers. And if we have a standard population that fills up the universe, say galaxy clusters, then we have standard population. In addition to these cosmological observations, we also obtain measurements of the omega matter from local dynamics, a large-scale structure. We can then combine that with independent measurements of Hubble constant through the distance ladder process we talked about earlier, or ages of globular clusters that confine age of the universe. And so even though there are many couplings and degeneracies for any given method between different parameters, all of them converge to the same set of values. Because of this, we believe that we have a good picture now. Many different methods, completely different kinds of measurements, completely different kinds of physics, all converge to the same thing. And this is why we think that concordance cosmology is now fairly well established. Next time, we'll start talking about the early universe.